So, good morning, everyone, and welcome to this webinar and presentation. All of you know that we are now in the middle of the coronavirus crisis, which has gripped the entire world. So, it leaves us plenty of time, and we will try to make the most of it. So, in order to enrich our knowledge and to continue to maintain a connection between all of us. In Israel, as probably in the rest of the world, the entire population now is in a relatively quarantine. And as a dentist, our Ministry of Health instructed all of us to avoid any elective treatment, but we can still open the offices in order to make an emergency treatment. So most of the dental practices now in Israel are closed. And hope in the near future this will be changed. Today, we will talk about the new concept in the implant world and the big question to drill or not to drill, and to try to understand the cases where the method can be applied. During history, a lot of clinicians try to develop the ideal dental implant for replacement of tooth, root, or stabilization of the dentures. And thanks to the efforts and their daring and revolutionary thinking, we are now in place where a dental implant is a public domain and accessible to general public. In the past 50 years, many theories have been proposed regarding the perfect design of the perfect implant and the philosophies behind these proposals. And we saw amazing evolution that took place in the field. And step by step, we have seen now how small things in design make a big difference. And the question is whether they're a really winning design of perfect implants suitable for any patient, any region of the mouth, and suitable for any doctor with any type of experience, or all of them like the same. Are they really the same? So I think that to ask the question, what is the best implant? It's like to ask, what is the best car? Even this gorgeous car has some limitations, like a number of passengers, suitable roads, and the weight that it can carry, and so on. So we are very well aware that about the differences in the levels of the teeth, size, number of roots and cusps, different bone types of different jaws, different anatomy, and of course, different habits of the patients, like a self-care and bruxism, and of course, different clinician experience. So the question should be, what is the best implant? But what is the best implant for specific situation? A little story. A few years ago, during some discussion about drilling protocols and bone preservation, one of our partners, who is not a doctor, asked why not to create a self-drilling implant to avoid drilling and bone tissue sacrifice. So it was a stretch for him that we are drilling out the most valuable materials for the implant, and then we are fighting to restore its loss. So we laughed at him, of course, by not understanding anything about biology and the concepts like strain and stress of the bone. And we told him that he should shut up. But we should remember that dental implants are medical devices. And this is exactly the place when physics and biology meet together, and understanding and integrating those factors together affect the ultimate success of our treatment and our patients. And we should remember the expectations of our patients. The expectations are very simple. They want teeth, not implants. And they want teeth that will look and feel natural with as much as less invasive and painful procedures. So some time ago, a friend of mine, Professor Trizi from Italy, who was that time a member of Cortex advisory board, and didn't know about the previous suggestion of our partner from the past, mentioned that patient declaring that the drilling is the most traumatic experience in the whole treatment. And that why should we check the idea of drillless implant? We couldn't tell him that he doesn't understand the biology and stress and strain, and he just said, okay, can we check it out? So the challenge is to create design which will not increase dramatically the microstrain. So we started with this challenge, and we started with the planning with combination of all the elements that promise better osseointegration and function of the implant. So we should remember that successful implant has several factors, and it's important to remember that we can influence those factors in order to create a very high predictability. So factors which are influencing those integration are factors which are related to the implants, dynamics, and microstrain. So specific characteristic of the implants includes different surface treatment protocols, shape geometry, different materials and alloys, and of course, variable connection types. The surface actually, it's the key factor of clinical predictability. And it's actually assures us the success and survivability of the restoration over the time. We know a lot of protocols of different companies of surface treatment, and most of them are good and predictable, like Thionite of Nobel, also Speed of Astra, MTX of Zimmer, SLA of Straumann, Machined of Brennemar. And you can be impressed by the topography or morphology of these type of surfaces. But if you will look closer, you can see that only an SLA has a similarity with the bone morphology. So SLA actually acts exactly or looks exactly like a bone or very similar. It actually tells to the bone, hey, I'm exactly like you, let's integrate together. It's much more easier. And if we will examine the publication in the last 5 years in PubMed, we can see that there is a lot of different publications of different treatment protocols, and the number is quite big, which give them a good scientific basis. But if you will look at the number of the publication regarding the SLA surfaces, you can see that the scientific basis is much more larger and evident. So what is it SLA surface? Actually, it increases the surface envelope from 3 to 4 times and produces hybrid roughness, macro roughness of 20-40 microns, which regarded also glass size, and micro roughness of 1.5 to 2 microns, which regarded to the size of fibrin filaments. SLA is sandblasting with very precise particles of aluminum oxide and double acid etching process. So the advantage of this surface treatment is acceleration of implant osseointegration, improvement of primary stability, shortening of regenerative period, and high degree of prognosis. So now you can see this short video which explains the process of the XRA surface treatment. After the treating it with the aluminum oxide particles, which have to be with the same size, hopefully with the largest machine with the big filters, then the acid etching actually cleans the residues of those particles and making a micropores of 1.5 to 2 microns. Second factor, it's a shape of the implant, geometric shape of the implant, and it has a great significance: compression, condensation, cutting, stability, loading forces, and so on. The platform shifting, of course, shift the transition between the implant and abutment to central position, thus keeps away mechanical and microbial irritants from the peri-implant tissues. The biological width moves from vertical to horizontal. Therefore, the modification of platforms is an important factor for the stability of tissues, but only in combination with the stable connection design and, of course, a good platform control. Here you can see some histological section, which Professor Trizi did years ago. It demonstrates a bone presence in the implant shoulder level and very nice soft tissue attachment to the horizontal surface of the shoulder. Platform shifting allows to place the implant in subcrestal position, or when we do not have a straight bone plane due to the emergence profile of the implant using hex connection, we will need to use bone profilers. Even when we are placing an implant in the bone level, but when we are using a tilt implant like in all 4 procedures, even then, a part of the implant, a distal implant, will be in subcrestal position. And it makes very difficult to place abutment without bone profilers. And any one of you which place an implant in this type of position knows how difficult it is to find the position of the abutment to reduce the bone around the implant in order to sit the abutment until the end. So in that case, conical connection and platform shifting allows us actually to lateralize the gap, the emergence profile of the abutment. And in that case, we just can choose the abutment with a little bit higher neck, and then to avoid any usage of bone profilers and escape all these troubles. Materials is a very important factor of the implant, and we know a lot of materials from the past and even from the present. In the present, we have some materials like tantalum of Zimmer trabecular implants, titanium, zirconia of rock solid of Straumann. Commercially pure titanium, it's still the most usable alloy in the market, more than 80% of the global market. Sorry, not commercially pure, titanium alloy. Commercially pure titanium, it's a minority, of course. And zirconia implants, which are in the market for at least 30 years, but still they cannot make a big market because of the troubles that they are creating with the connection with the prosthetics. Connection types, different connection types during the history. In the recent years, most of the connection types narrowed to 2, like a conical and internal hex connection, because of the experience that we have with the connections over the time. And of course, this very interesting research of Zipri from Frankfurt University have shown us the micro gap in between the abutment and implant interface after the loading on the abutment with the 100 newtons and 200 newtons. And you can see the micro gap which exists almost in all the connection types, especially when we had two flat surfaces in the interface, like trilobe, etc. The single connection, which didn't show any micro gap, were of connection types of Astra and Ankylos. Maybe that is explaining the reason that most of the dentists in recent years moves from other connection types to the conical connection type, even though it was a little bit more difficult for the restorative dentist or prosthetic prosthodontist to restore with the connection types, conical connection types, but still we see the tendency that most of the doctors recently moving to this connection. And why is that? Because of the advantages that it has comparing to other connections like internal hexagon. The micro gap, for example, is formed between the implant and the abutment, and it increases the lateral forces which are placed on the abutment. So micro gap actually is formed by elastic deformation of the implant wall. Another factor or another thing that Zipprich showed, it's a phenomenon of micropan. It's additional factor of micro movements that is a pumping effect, especially in the implants and abutments, which has large cavities or spaces in their interface. So the micropump form when there's a lot of space and the micro gap open during the chewing, so all the liquids actually are pumps in and out and creates a very nice media for bacterial growth. Screw loosening, it leads to increase in micro gap, and it leads, of course, to inflammation and bone loss. In external hex, for example, in the past, we faced about 60% of screw loosening comparing to 6% of internal connection, which conical connection, it's even less. And why is that? Because in conical connection, tension, it's not going onto the screw. The conical portion actually it's screwing down into the implant and create forces or separate forces on the implant walls which try to rebound back and locking themselves on the abutment surface. So all the tension actually it stays in abutment implant interface and less on the screw. And this slide it's representing it very nicely. By accident, we discovered it because we was trying to see the behavior of the small multi-unit abutment. We were very worried about it because they are very small. They have 1.4 millimeter diameter, and we wanted to see how they will behave in the fatigue test. So we applied the fatigue test and we saw that the fracture point was not on the screw or the mini screw of the multi-unit abutment, but on the connection of the abutment with the implant interface. And this is the best thing that could happen because when we are thinking about the implant, we want to think about it as a device for the lifetime. The prosthetics we can change, restorative work we can change, but it's expensive. It requires sessions and visits to the practice to involve the lab in the process. But abutment, it's the most easiest part to exchange because we just can choose it from the catalog and to replace it and swap. And here the fractures on the fatigue test actually, in all the cases, happened on the abutment interface. And you can see that it happens on 280 newtons, which is very high, which is very high level to comparative to the internal hexagon connection. And we are speaking about the worst scenario. Worst scenario, we are meaning the longest abutment, the biggest angulation, and the narrowest implant. So we use it with a 5 millimeter neck of multi-unit abutment, 3.3 millimeter dental implant, and 30 degrees angulation. So we saw that conical connection sustained this stress up to 280 newtons comparative to internal hexagon connection, which sustained it only to 130 newtons. And look where the fracture happens on the internal hexagon connection, not on the abutment, but in the worst place that we ever want to expect it, on the implant neck. The next factor, which is influencing also integration, the micro movement, the interface. And we can know in our practice when and what can we load. Not always, because the good primary stability actually it's limiting the micro movement up to 50 to 150 microns. And actually, we don't have any tools in our practice to measure this type of micro movement. We cannot feel it. We can just use some tools which can give us some clue about the micro movement or not. So the primary stability is important, and we see so in recent years that the tendency is to reduce the number of implants. If 20 years ago we were using a concept almost implant per a tooth, now we can see a lot of works with a very good success of all-on-4 and all-on-6 concepts. Maybe in the future we will see a concept all-of-1 with this type of implant. But primary stability is a big issue. And we should remember that we are not working with wood. We're working with the material which is response to trauma, response to load, injures, heals, resorbs. So primary stability appears to be a big issue in the moment. And why is that? Because we have driven our shift in protocol from delay loading to immediate loading. Immediate loading, immediate placement, and immediate loading, it's a very big, challenging biological environment. And primary stability associated with mechanical engagement of the implant with the surrounding bone, where bone regeneration and remodeling phenomena determine the secondary biological stability to the implant. So the timing in between them creates a dip. This is a stability dip, or we can call it a failure dip. So the literature suggests that there is a critical threshold of micromotion above which fibrous encapsulation prevails over osseointegration. So this critical level, however, was not zero micromovement, and there is a tolerated micromotion threshold that was found to be as a 50 to 150 microns, as we told before. So is there any possibilities or ways to enhance the stability and obliterate the gap? Yes, there are. For example, we can increase the total stability by acting on the implant level. We can increase the implant number. We can split the implant in between them. We can use proper implant shapes or implant designs to use longer implant, wider implant, conical implant instead of cylindrical implant, and so on. Or we can enhance the primary stability by acting on the implant level. We can enhance the primary stability by acting on the bone level. So we can use the bicortical implant placement. We can use bone condensation techniques. We can use special implant design like Saturn, Magix, etc. We can enhance the secondary stability by acting on the implant surface. So the secondary stability will take place sooner if we will use a specific surface treatment implants like SLA on in the future nanotechnology, which now in stages of researches in many places. So maybe we will see some integration of calcium triphosphate particles on the surface of the implant, which will stay stable and which will enhance the bone response. So probably we will see those in the future. So primary stability insertion torque, maybe it's the biggest worry of the dentists which are using the high torque insertion torque, high torque implant placement. And the question if it may cause some problems or not. So there are a lot of literature regarding the high insertion torque. And one of them says that immediate loading is considered valid therapeutic choice even in low density bone, as long as at least 45 Newton per centimeter of insertion torque is reached. Of course, it's not recommended to use immediate loading on D4 type bone, but in D3, if you are reaching more than 45 Newton per centimeter, usually you will not face any problem. And what is it exactly immediate loading? By definition, in 2003, in the consensus conference in Switzerland, set as a limit of 48 hours after implant replacement. So the rationale for immediate loading, there is a lot of rationale. So some of the rules not should be followed, but it's known more than for 30 years that mechanical stimulus of the bone accelerates the bone repair and stimulates osteogenesis with higher quality of bone around the implant. The next, which is influencing osseointegration, it's biomechanical factors or microstrains in physiologic range. And it's also a new topic. In 88, Frost represented in orthopedics this table where he measures the strain of the bone and the bone response because of the strain. And he imparted to this table disuse when actually we're having atrophy of the bone if the strain is lower than 400 microstrains. So we will face a bone resorption. We will keep the physiological range of the bone if we will keep physiolocal load, which is between 400 to 1,500 microstrain. If we will overload it a little bit up to 2,500 microstrain, we will have even increase in the bone mass. And of course, more than that, more than 2,500 will lead to bone resorption. It's a pathological overload, and even more than that, to bone fracture. So microstrain in physiological range, and even a little bit more than that, stimulates the bone. It leads to good mineralization of the collagen, and even making a better qualitatively in the peri-implant bone and the tissues. So in the last decade, primary cilium was found as a mechanosensor, and is actually it's a novel extracellular sensor in the bone that grows from the centriole of osteocyte and extends into the extracellular space. And it reacts to the fluid flow. When it bends, when the fluid flow is too big, it bends, actually it gives a signal for the bone response, which will be as a bone resorption. So knowing those factors and now having the abilities to measuring it in our laboratories, we decided to make a few prototypes of the implants and to go with them through different tests. In the end, we left only two designs to the final test, which were more expensive and more time consuming. And we checked them out with the control implant of dynamics. So the tests have been done with the Professor Zev Ormianer in Tel Aviv University, which is now a chief of prosthodontic of oral rehabilitation department. And after doing the tests, we decided to launch the implant, and it was launched in IDS several years ago. I will explain you a little bit about the test that we have done. In the test, we arrived with two types of implants, new implants, type 1 and type 2, and type 3 was a control implant of dynamics. We inserted the bone strain gauges into the bone. It was the bovine cortical big bone, and we measured insertion with the minimal drilling, with no drilling of the new implants, and with the drilling by the protocol of dynamic implants. And we measured the strain with the insertion, and 24 hours later to see the recovery. So the results were very interesting. So we saw that the higher vertical compared to horizontal strain was on type 1, type 2. The higher horizontal strain was in type 3 dynamics implant during drilling and insertion. Type 2 implants show the lowest strain levels of all the groups, and the highest horizontal strain levels were measured with the insertion of type 3 implant. So after 24 hours, we checked the stress release, and we saw that the least prominent strain recovery, insertion horizontal strain of type 3 implants, of dynamics implant. This article was published recently, and the conclusion was that drilless implant presented favorable vertical and horizontal strain distribution compared to regular protocol. Residual strain was low within all the dimensions of bone. Conventional implant insertion delivers strain around the implant neck. Horizontal residual strain, both in drilling and inserting conventional implants, was higher than the horizontal insertion strain of the drillless implant. Surface roughness measurements didn't show any difference. Surface roughness measurements, it was another study within the same study, because we were worried what's going to happen to the implant surface if we will apply a high strain without almost drilling at all. So probably it will ruin the topography of the surface. So we did some tests in microscopic, in electronic microscope, and we used the implant with very high torque, and then we measured the Rx and SA and RA values. So the conclusion was also that the SA and Rx result didn't diverge from the normal value of the implant. The difference was not significant at all. So, because of those results, we choose the type 2 as a implant design, which we'll continue with it, and it's called now Magix, and it includes a lot of important parameters in the surface, like flat neck, angle external 1 degree angle external walls. So it looks very conical, but external walls are almost cylindrical, so it making a better condensation of the bone around it. It works like actually bone expander. Conical and platform shifting, and you can see on the right that actually implant it drills itself and pushes itself into the bone because of a very sharp first thread, which enlarges and condenses the bone vertically and horizontally. So we was worried because of the shape of the implant if we will not lose the surface comparative to the regular implants. So we made the measures of that, and you can see that the surface area, it remains almost the same. Maybe in the narrower implants, it's a little bit bigger with a conventional implant, but as much as it goes longer, it's getting the same. And in the wider implants, the Magix implant even has a bigger surface than the conventional implant because of the deep thread design. So we try to use this implant in different bone types. So you can see in the soft bone, only with the marking tool, the implant actually expands the bone and releases the bone tube, which it cannot condense inside the bone tube going out, so we actually can collect the bone. It was in dense bone. So in soft bone, in the test, even without the drilling, you can see that it condenses all the bone around it, impacts it, and enlarges the bone volume. We performed study on the rabbits for histology also in Apollonia University in Romania, together with Tel Aviv University from Israel. And we used this Magix implant with two different protocols, comparing with conventional protocol of the dynamics implant. In the Magix 1, for example, or Magix 2, it's the same implant, but different protocols. In the first one, we used only a marking drill on the left side, as you can see, and inserted the implant to all the way down. It was a bicortical connection because the rabbit tibia, it's very narrow, so we had to go deeper. Then, on the second protocol, we used mark drill all the way down, and with the 3.7 millimeters, just perforating the cortical bone on the upper part of the implant. And the third control study was with the dynamics, with the whole sequence of the treatment. And we can see that the torque was almost similar for two test groups, and the control group had higher torque because of bicortical connection, and the apex of the conventional implant, it's larger. So, of course, the torque was higher by penetrating the second plate of the tibia of the rabbit. The bone to implant contact values for Magix 1, just with the just with the marking drill, didn't change between 21 and 42 weeks. 21 weeks, it's like similar to 2 months of human, and for the 2 weeks, it's similar to 4 months at human. And in test 2, when we perforated the cortical bone with 3.7 millimeter drill, the bone to implant contact was lower after 21 weeks, but restored after 42 weeks. And it means that it has, for group 1, had better stability during the healing period. Control group with the dynamics implant had a lower stability at 21 weeks and improved after 42 weeks, but in overall it was lower than 2 Magix groups. The histology you can see after 21 weeks and then after 42 weeks, and you can see in histology section that there is no significant difference between all of the group. The difference is that the primary stability of the implant with just the marking drill was higher during the recovery period or healing period. So the advantages of drillless approach is that it has a less risk for bone perforation or fenestration. We preserving the bone and not throwing it out. We are condensing the bone, which improves the quality on per implant bone and tissues. We are increasing the primary stability, and of course, it's a more attractive approach for novice clinicians. We should see and look at this design of drill of bone expanders, and it looks like the same, or acts like the same, but instead of having one more additional kit on our surgical field, which needs to be taken care of, sterilization, etc., the implant doing the work by itself. So the insertion of the implant, like you see now in the video, it's to start with inclination to the lingual position and then straightening it up. The implant has an amazing ability to change the direction during the insertion, even when most of it already embedded into the bone. We still change the position. It condenses the bone in creating a cuff of fractured condensed trabecular bone around the implant, which actually improves the bone quality. In order not to lose the direction completely, we are suggesting to use drilling with an implants, and it depends of the bone type. In soft bone, it's enough only with the pilot. In more dense bone, we should go further. That allows us to control the implant positioning axis and not to lose it, because implant will choose usually to run away to the softer bone or to the void spaces. At the beginning, we thought to use this implant only for the upper jaws, because only in the upper jaw we have the ability to use the screwdriver and to control the insertion path. But we saw that it can be used very, very well in the lower bone also. Of course, we have to take in consideration the bone quality and to behave accordingly. Here you can see some video of the lower bone implant placement in the 36th position with just pilot drilling. Of course, today I would use the T-base to make this temporary crown and not to conventional implant or conventional abutment with this type of modification. So you can be impressed of the X-rays immediately after implant placement and after the healing period, and you can see that within the immediate temporization, actually we can manage the contour of our gingiva to maintain the volume of all the surrounding tissues. Some more examples of Magix implant. Those x-rays were provided by a friend of mine, Dr. Lasri from Paris. And you can see a very nice bone remodeling around the implants and platform shifting. And in most of the cases, you can see the bone growth on the shoulder of the implant. So in the end, sorry, this is the trial at the beginning when we did in the soft bone without drilling at all. And you can see that in the soft bone, the insertion torque reaches up to 60 newtons. And you see how it expands the bone, condenses it around the implant, giving us a very high primary stability. With a medium bone type, like D2, D3, it's 1.5 millimeter drilling, and you can see the insertion of the implant. With also 60 newton, it can reach more. You can drill with a pilot, and it will go easier. You see with the motor, it goes almost all the way down. And then try to move a little bit with the hand length. In dense bone type, pilot drilling, the insertion torque is higher. You can more than you can use even the next drill 2.8, or just to release the stress from the vertical part with a larger drill. Now, don't have to go all the way down. And you can see the implant, it starts already here, and from here with the hand rail. Now, when you are reaching the high torque values, you can go forward and backward in order to release the stress. As previously I showed, now you can see slowly what it's doing to the bone, how it enlarges and expands. You can see the change in the volume of the bone around the implant. So actually we are preserving all the bone around the implant and its volume. Now, this is one more case. We should place an implant in this 1-4 position. And after flap elevation, you see the bone loss, horizontal bone loss, buccolingual bone loss around the implant. After insertion of the implant, actually, you can see the difference in the bone volume around the implant itself. So actually it saves us the needs of making bone augmentation in order to restore the bone volume around the implant. And this is the same case after the healing period, and you can see a very nice emergence profile around the restoration. Even in this worst scenario cases, when we do not have at all the buckle plate, and we have to make immediate loading because the patient refuses to go with some removable flicker or with no tooth. So immediately after extraction, this implant allows us to achieve a very high primary stability. So as you can see here, we are placing an implant, simultaneously we are making a bone augmentation with a membrane and immediate restoration with a temporary crown. And you can see very nice healing, very nice emergence profile and soft tissue color and health. And on the X-ray, you can be impressed of the bone growth on the shoulder of the implant. So the effect of high insertion torque versus low insertion torque on marginal bone resorption and implant failure. This is a very nice meta-analysis of 760 articles, which were been done by an Italian group of doctors. And their conclusion was that the current review indicated that there is no significant difference in marginal bone resorption and implant failure rate between implants inserted with high or low insertion torque values. So high insertion torque do not lead to the risk. High insertion torque does not induce adverse reaction in cortical bone and does not lead to the implant failure. Another study. So by creating this bone condension, it works, as I told you, like bone condenser. And how it condenses, it's fracturing the trabecula and condensing it around the implant. It actually works like also densification. And this study, which was done by drilling Versa drills of also densification, they've been shown that it actually increases the bone volume. This study was done by our Cortex. So at the beginning, when we presented this concept, we met a lot of very suspicious reaction, or a very skeptic reaction. And it reminds me this say of Arthur Schopenhauer, which told us that all truth passes through three stages. First, it is ridiculed. Second, it's violently opposed. And third, it's accepted as being self-evident. This promotion video for the new concept of the new Magix implants, which is not new anymore. So this is the end of presentation. You can leave to all participants my email address, if any one of them, or my messenger. You can find me on Facebook, send me messages about the presentation or any other question about any other Cortex product. I will be more than happy to reply to you all.